Okay, hello everyone. Welcome to today's NPTEL discussion session again for this Coherence and Quantum Entanglement course. And this is the week 8 where we will discuss several topics, several more things, and we'll solve many problems as we always do. But before that, let us wait for few minutes such that other people also join uh, in between. You can check your previous things, and I will also again tell, and then we'll start. Today mostly I will focus on problem solving because many of the students are telling that they are finding it very problematic to solve the assignments. Our main focus will be to uh, do the problems more rather than discussing more and more new stuffs and more research work stuff, and rather discussing the theory again and again. We need to know the theory as well as we need to solve the problems. Our focus will be on the problems, but of course I will revisit the week 8 topics which are discussed in your lectures, and then I will start for the other things as we always do. So let us wait for a few more minutes such that other students, other people also join, and then we will start the session. I'm extremely sorry for the background noise. I don't know, in some other block construction is going on, so it is problematic. I am extremely sorry for the background noise, but please be considerate with that. And I cannot do much about that. So let's avoid try to avoid that. But the today's video is going to be a bit. Noisy and for the background noise, I'm extremely sorry for that. Okay, so I was supposed to start within 2 3 minutes, but as many of you people have not joined yet, so let us wait for few minutes more and then I will start. Okay, so let us start today's discussion. It's our today's discussion. This is the NPTEL session for coherence and quantum entanglement, where this is the week 8. Today is 16th March, and after completing today's class, we are going to complete two-third part of the total. Two-third part of the total semester course of this NPT of this season. So as by this time you guys all are aware about I am your TA, all are aware me. I am your TA Nilakshi Shanapati, and this is the course offered by NPTEL through SWAYAM portal. Course title as Coherence and Quantum Entanglement, instructed by Professor Anand Kumar Jha. So these are the problem solving sessions which used to happen on every Saturday 5 p.m. to 7 p.m. All right. So 5 p.m. to 7 p.m. and this is the week 8. So we are going to start today's discussion. All right. So you in this week 8, what was covered in the what was covered in the lectures was mainly the Hong-Ou-Mandel effect, which happens which we observe uh, with the two photon interference effects that comes from spontaneous parametric down conversion or SPDC. Sorry. So I have already told or introduced about what is two photon one photon we are already you are already aware about one photon interference, two photon interference, spontaneous parametric down conversion, the nonlinear processes. All are well discussed in the lectures as well as in the discussion sessions, and all of the equations I have also showed you, whereas in the lectures it was derived with uh, with the explanation for each and every steps. Okay, so finally what we learned in the previous class, that what is the coincidence count rate, and which was represented with the RSI for the down from coming from the down converted fields, down converted field that was generated through a nonlinear optical process. And before that we have learned about all of the basics of all of the basics that was required for this course, like coherence in the temporal domain, spatial domain, and everything, and orbital angular momentum domain, polarization domain, etc. So today I will solve some problem on polarization basis again, and then we will solve some problem from the one photon, two photon, and so on. So one by one we are going to solve these things. And mostly I try not to do those questions which are given for this week's assignments, such that you guys can try by yourself and do not follow what I am doing and just put the answer there. But as many of you are writing in the question answer session, so if you have any problem in understanding of any of the questions that was given in the assignments and you want to discuss with us, then you always feel free to discuss those things. As well as mostly the questions which were there in the assignments, those are discussed in one way or other way in these classes, in these discussion sessions. That is the main aim of doing this kind of discussion sessions which are arranged by the NPTEL. So it will be very nice if you guys follow the lectures as well as the discussion sessions simultaneously. Okay, so all right. So again, coming back to the thing which we are discussing, that we observed the two photon interference is observed, and we got the coincidence count rate as delta, which is a function of delta L and delta L dash. Those are the path length difference and path asymmetry, right? And finally now we will discuss about the Hong-Ou-Mandel interference, which was discussed already in the in your lectures. So as illustrated in this figure, which you can show in this 1 minute, which you can show which you can see in this slide which I am presenting, that this is the Hong-Ou-Mandel experiment setup. The signal and idler photons from the parametric down conversion or PDC are mixed at a beam splitter. I hope you guys can see my picture, what it is showing. That pump is coming, it is going through this PDC and producing signal and idler, and they are then mixed at a beam splitter, and the two photon interference effect is observed in the coincidence count rate of detectors DS and DI. I have already mentioned what is coincidence count rate, and what are DS and DI are the detectors. But still, let me tell you again that coincidence we will get when, suppose a photon is coming, a photon is coming and falling on the detector, and it is being detected at t1 time, at t time, at the detector ds, then the detector then the second photon is simultaneously detected in the di, that is the detector I, in the idler photon, for the idler photon at at t plus tau or time. Then that it's then the simultaneous measurement of presence of those photons are called the coincidence. Now and that tau which I am talking about, that tau should be very smaller, on the scale of nanosecond or picosecond, then only you can detect the coincidence count. So finally, we know what is the coincidence count. I have mentioned in the previous class also. Again I mentioned for just to revise that. Now coming back to the Hong-Ou-Mandel effect. So after mixing at the beam splitter, and the two photon interference effect is observed in the coincidence count rate of detected dsdi as a function of beam splitter position x. Now the experiment can be understood in terms of two photon path diagram, which is shown in in this downside figure. You can see that only interference can occur for these two paths, which are shown with 1 and 2. If it goes from this, signal is going to this and passing through this from the beam splitter, transmitting through the like reflecting to the beam splitter, then it will follow this path 1. And if it is transmitting through it, then both of the thing, then it will follow the path 2. Then only the coincidence, both the coincidence can be observed. If one of them are reaching and another one is not reaching, that means there something will there we are missing something. And those cases are not those cases are arriving when it within the when the signal photon is arriving, but the other photon is not arriving within the time window tau. Okay, so these are the two paths, two cases when the two photons can be detected simultaneously. In alternative one, both the signal and hydrogen photons get reflected by the beam splitter, as I said, and for the alternative 2, both get transmitted by the beam splitter. Now, using this two photon path diagram, we find that for this case, delta L equal to 0 and delta L dash equal to 4x cos theta, where x is the displacement of the beam splitter. Now this, how we can find the delta L and delta L dash, those formulas are already discussed in the previous class as well as the lecture. You can find it by yourself. Now as del L equal to 0 and del L dash equal to 4x cos theta and delta phi equal to pi for this case, so the coincidence count rate RSI for this case, I have written wrong here. This will be C into 1 minus gamma dash 4x cos theta. This will not be the thing. Not gamma d. Let 1 minute. Wait. Actually, this equation which I have written here, this is for the postponed compensated effect for the Hong-Ou-Mandel. So this is not the correct equation. By chancely I have written for this Hong-Ou-Mandel. This will be rather the equation will be RSI equal to C into 1 minus gamma dash 4x cos theta and nothing else, because delta L equal to 0 and delta L dash will be 4x cos theta and delta phi is equal to pi. Okay, so this is my mistake. I am very sorry for that. This equation need to be modified. This is for the postponed compensation for the Hong-Ou-Mandel effect. Now what you are seeing here, that is the Hong-Ou-Mandel effect. For that, delta L equal to 0 and delta L dash equal to 4x cos theta and delta phi equal to let me rather remove it. Yes, so okay, for this case you can find the delta L dash and delta phi, which are already discussed in the classes in the lecture. So this will be the RSI after all of this calculation. At x equal to 0, that is at the balanced position of the beam splitter, the coincidence count rate RSI is equal to 0. This implies that at the balanced position of the beam splitter, both photons always leave through the same output port of the beam splitter. Do you understand? At x equal to 0, that is at the balanced position of the beam splitter, the coincidence count rate will be equal to 0. That you can see, right? Gamma dash 4x cos theta x equal to 0 means gamma dash 0. This implies the gamma and gamma dash 0 means 1. That means 1 minus 1 equal to 0. RSI will be 0. This implies that at the balanced position of the beam splitter, both photons always leave through the same output port of the beam splitter. As a result, a null is observed in the coincidence count rate at the balanced position, leading to a dip in the coincidence count rate as a function of the beam splitter position x. Okay. And there is a concept of bunching and anti-bunching of photon. People used to describe this thing in terms of an intuitive explanation of this effect, which can be told as bunching of signal and idler photons at a beam splitter. So if you want, then I can provide you with the original paper of Hong-Ou-Mandel, where you can go through the details to study it. But okay, but nonetheless, there are so this is the effect which you can observe, and which is a two photon interference effect, and this effect is called the Hong-Ou-Mandel effect. Now this Hong-Ou-Mandel effect was described in terms of bunching of entangled photon at a beam splitter. But the bunching interpretation is not adequate for some other experiments which actually can be through which we actually can see the Hong-Ou-Mandel dip, but that is not actually Hong-Ou-Mandel, rather some post processing or some postponed compensation or some induced effect has been done. And in those kind of experiments, Hong-Ou-Mandel like effects are observed even when signal and idler photons do not simultaneously arrive at a beam splitter. And if you are given with any kind of problems for those, you just for solving the problems for the two photon interference effect, you just need to find out the delta L dash. Those are the mainly two photon path difference and two photon path asymmetry. If you can find all of you can, if you just calculate those, and if you find out the delta phi, that is a phase difference between the two paths, then you can easily find out the coincidence count rate for this kind of experiments. And why I am focusing on these things so much, because even current research is on based on all of this. Even when we do the things, we actually for studying or doing anything with the entangled photon, with the quantum entangled photon, then we always do this kind of analysis in case of interferometry setup. Okay, so that's why it is very important. And this is the Hong-Ou-Mandel effect, very important. And there can be but this bunching anti-bunching concept is not so viable in the postponed compensated Hong-Ou-Mandel effect as well as induced coherence effect. There we can also see the Hong-Ou-Mandel dip, where the simultaneous arrival of signal and idler are not true. But let us not go into that detail. Maybe whoever is interested to study more on these and want to pursue research in this area, then maybe you can contact me. I can provide you with the papers that you need to follow. Okay, but before actually, in case of other classes, whenever I start our discussion session, we mostly start with the detail of these informations, like where I am going to where you are going to get all of these notes and everything. So today I forgot to tell you once again about those things, because I know you guys are well aware about all of these things now, all of these technical things now, that but still again let me give you all of these references first is that this is the drive folder link where I am going to upload all of these lecture notes, class notes, and whatever I am going to teach you, all of those all of the material you will get from this, and as well the some these slides, and this some more problems, sometimes some videos, sometimes uh, some paper or something which will help you to understand that better. Many thing I actually used to upload there, and this link is already shared with you through the SWAYAM portal by NPTEL. But again I am giving you the thing, and there is a Excel sheet where the YouTube link corresponding to its weeks, the presentation folder link, and everything is given, which you can see. This is a one-stop place where you can find everything. That's why it is made, and it is again you can find through in the SWAYAM portal of NPTEL. And finally I will show you the YouTube channel link, where you can get the videos of these classes. So this is the YouTube channel link. All right, so these are very important, as every time I used to tell you guys, so again I just mentioned them once. All right, so now I will start now I will start it, the like problem solving things, like several problems we will solve and discuss. Those things I will start to discuss. But before that I just want to tell one more thing, that is that several things we are discussing in case of two photon parametric down conversion in the temporal degree of freedom. Now similarly you can do all of these things in the spatial degree of freedom, orbital angular momentum degree of freedom. Everything can be done in any degree of freedom. If, like even you can study it in the polarization degree of freedom. So those things are there. And now all of this was the background of the mainly the nonlinear optics effect through which we can and this process spontaneous parametric down conversion through which we can actually generate a quantum entangled photon. But now we need to go deeper with the ideas that what is actually quantum entangled, can the how the concept came and why it became so blooming area right now, and can the quantum mechanical description of physical reality be considered complete or not, how those kind of questions were answered with the generation of SPDC photon. Those discussion will do. So before that, today our main goal is to solve many problems. So maybe I can give you a glimpse of these things, such that you can visit and remember what are the things in the upcoming class, such that you will get more interest. So for that reason maybe I can give you one paper link, because till now you guys must have heard about Einstein Podolsky Rosen paper, which is a very popular paper, where you can get the idea where actually they told about that quantum mechanical description of physical reality is not complete, and quantum mechanics should be rebuilt again. For those and from that, at that moment the concept of hidden variable theory arose. Now after that, one by one step, from the 1935 to its 2024, it is very well established that at that moment Einstein Podolsky Rosen were wrong, and it was right from their perspective, but the quantum mechanical weirdness is actually true, and it is actually the ultimate truth. So so the main weirdness journey starts from here, week 8. So we'll discuss about those things which are actually very interesting for all of you. We'll discuss about many how one by one everything discarded, and quantum entanglement come into the role, come into the play, whatever you say. and then we will discuss about quantum teleportation, quantum information, Eckert protocol, BB84 protocol, kind of protocols, quantum information network, all of those things. Even we can discuss some other phenomena also, what is actually going on in the current scenario, and mostly quantum information, quantum communication, quantum teleportation. There are many things which are already established, currently going on, and how we do those things, what are those things, all of the things we will discuss. Okay, I can give you the paper which was by Einstein, Podolsky and Rosen, from where the this question arised, that if this question arose that can the quantum mechanical description of physical reality be considered complete. So this is a paper link, this is a not link, this is a paper details. This was a physical review paper from 1935, and in this paper EPR, Einstein, Podolsky, Rosen, so short from they are called as EPR, presented an argument to show that the quantum mechanical description of physical reality is not complete. And in this paper, EPR has recognized a spooky feature in the quantum description of physical reality, which is called as spooky action at a distance for the entanglement. They have mentioned like this. But this feature, now known as entanglement, which was originally called by Schrodinger something like Verstrangwang, I don't know what is the exact pronunciation of that. So something was that which means entanglement, and which implies the existence of global states of a composite system that cannot be described as a product of the states of the individual subsystems. For an extensive review of the subject of quantum entanglement, we can see another paper that I can give you. This I forgot exactly which paper it was, but I remember the paper author name. It was Horodeki et al., which where you can get all of this extensive review of the subject quantum entanglement, and this is a very nice paper. Okay, so we'll discuss them, but before that we are going to solve the problems for today, that is our main aim. So let us wait, let us take rest for 5 minutes, and then we'll start solving problems. Okay, so let us start our discussion with the problem 1. You you first read the question very carefully and then start solving one by one. This was already there uh, in your assignment, some part of it. So now we will solve that. So let us read this question first. So it is saying, consider three independent uncorrelated fields. The first one is horizontally polarized, the second one is vertically polarized, and the third one is polarized along 45 degree. If the three fields are incoherently mixed in equal proportion, what is the degree of polarization of the resultant field? Let us do so whatever it is mentioned. Okay, so what it is saying, read once again. Consider three independent uncorrelated fields. The first one is horizontally polarized, the second one is vertically polarized, and the third one is polarized along 45 degree. If the three fields are incoherently mixed in equal proportion, that is, what is the degree of polarization of the resultant field? The polarization matrix J, first we will write that. Now we know the formula of degree of polarization, so we will use that to know what is the degree of polarization for this above field. And this is for the like as it is mentioned that horizontally polarized, vertically polarized, and 45-degree polarized. Along with that, we have written the stuffs. I told you guys to learn about the Jones matrices for these things. Okay, so the degree of polarization, we will find it now. Now for this above state, trace of j equal to 1, determinant of j equal to 8 by 36. Therefore, we have p equal to 1 minus 4 determinant of J. Sorry, what will be the determinant? Okay, so this is the part A. Now the part B is saying consider the three independent so finally, it was asked that if the three fields are incoherently mixed in equal proportion, that's why one third, one third, one third, and what is the degree of polarization of the resultant field? So degree of polarization, we are using the formula and we are finding it, which is one third. Now part B. Consider three independent uncorrelated fields. The first one is horizontally polarized, the second one is vertically polarized, and the third one is polarized along 45 degree. If the three fields are incoherently mixed in 1:1:2 proportion, what is the degree of polarization of the resultant field? So the polarization matrix of the result of the mixture, I hope you guys can see my screen. So this is the polarization matrix in 1:1:2 format. Then the total, if we sum it up, then it becomes something like this, which it which which becomes even more, we can write it like this. You know the formula. One by 4 minus 1 by 36. Sorry, 1 by 16. Three by 16. So it will eventually become 1 minus 4 into 3 by 16 all to the power half, which is 1 by 4 all to the power half equal to 1 by 2. Okay. So this is the answer, the degree of polarization of the resultant field. Now part C, it is saying consider two separate suppose these are two independent lasers. Suppose there are two independent lasers with polarizations along horizontal and vertical directions. In what proportion the two lasers should be mixed such that the degree of polarization of the resultant field is 0.8? Let us solve that. The polarization matrix J of a state having the degree of polarization P can be written like P into J polarized 1 minus P J unpolarized. These are unit trace, so unit completely polarized and completely unpolarized polarization matrix respectively. So J unpolarized half 0 0 half. So one possible solution is by using the horizontally polarized light as J polarized unit, that is J pole unit equal to 1 0 0 0. Since it is mentioned that P equal to 0.8, so we get J equal to 0.8 1 0 0 0 plus 1 minus 0.8 half 0 0 half, which in turns can be written as 0.9 1 0 0 0 plus 0.10001. Therefore, the one possible solution is that we add the horizontal polarized light and vertical polarized light in 90:10 proportion. Another possible solution is that we add the vertically polarized light field and the horizontally polarized light field in 90:10 proportion. Another possible solution is that we add the vertically polarized light field and horizontally polarized light field in the 90:10 proportion. Okay. So these are the answer. Now problem 2. Consider two separate and uncorrelated lasers. The field from the first laser is polarized along x direction, whereas the field from the other one is polarized along theta direction. The two lasers are mixed at a beam splitter in equal proportion. What is the degree of polarization of the resultant field? What is the degree of polarization when theta equal to 0? What is the degree of polarization when theta equal to pi by 2? This is very easy. We know the formulation, we know the normal notation what we use. So on the base on that, whatever the normal whatever the notation we use, in terms of that, if we write what is the degree of polarization, 1 minute, what is the degree of polarization, then this but okay, let us not go into the normal formulation and all of those. Let us discuss very in step by step manner, because today's focus is only that, because otherwise like you guys are finding assignments are difficult. So let us start. So the electric field corresponding to the first laser, which is polarized along x direction, that can be written as u1 equal to u1x x cap plus u1y y cap, which is normally x cap. That means ex u1x equal to 1, u1y equal to 0. Similarly, the electric field corresponding to the first laser, which is polarized along second laser, which similarly, the other one which is polarized along theta direction, that can be written as u1 x cap plus u1 y cap cos theta x cap plus sin theta y cap e1 x equal to cos theta, e1 y equal to sin theta. Then the polarization matrix corresponding to these two fields can be written like maybe I should write it too. Okay, so J1 will be E1 x star E1 x, E1 x star E1 y, E1 x E1 y star, E1 y star E1 y is equal to 1 0 0 0 from these two. Similarly, from J2, E2 x star E2 x, E2 x star E2 y, E2 y star E2 x, E2 y star E2 y, that is equal to cos square theta cos theta sin theta cos theta sin square theta. Now, since these two lasers are independent of each other, the two fields will mix in an incoherent manner. Therefore, the resultant field is partially polarized field. And is given by J, which is equal to J1 plus J2. Okay. So now 1 0 0 0 plus cos square theta cos theta sin theta cos theta sin square theta equal to 1 plus cos square theta cos theta sin theta cos theta sin square theta. So now we can calculate, like whatever the scenario was given, we reach to the J matrix, it is the polarization matrix for that scenario. Now we need to calculate the degree of polarization for that. Okay. So this is the question: what is the degree of field, degree of polarization of the resultant field that is shown here. Now part B and part C is very easy to find out. It is told for theta equal to 0, what will be the P1 for the case B. Then theta equal to 0 implies P equal to 1. That is perfectly polarized light. Theta equal to pi by 2, P equal to 0, perfectly unpolarized light. Okay, so this was a question which we solved. I think you guys have understood. I have gone through very detail and I have gone through each and every step such that no problem arise and you can understand each and every step. Okay, I hope now these are very clear to all of you. And whoever has found problem, you can ask question through YouTube channel link, through the ask a question portal, and through my mail ID also. I usually share my YouTube, my mail ID with you also, such that you can reach to me according to your convenience. All right, so now we will discuss few more problems. Before that, let us take 2-3 minutes break. Okay, so let us solve the third problem now. Suppose that the state of photon is given as an incoherent mixture with equal proportion of states representing a horizontally polarized photon and a 45-degree polarized photon. What is the what is the probability that a photon in such a state gets detected as a 45-degree polarized photon? Okay, let us do so. So the state of the photon can be written in the horizontal or vertically polarized basis as rho equal to half 1000 plus half 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 equal to, it becomes very standard procedure that we are following for a while. So we now need to write the state in the 45 minus 45 basis, because it is told about that. So we need to move to that, and the corresponding unitary operator to go to that is nothing but 1 1 1 minus 1. So the state in the 45 minus 45 basis after changing from horizontal or vertical, we can write it in terms of rho dash u my inverse rho u. U are the unitary operator. U dagger rho u. Here we have used that the fact for unitary operator u minus 1 equal to u dagger, unitary operator. I hope you guys remember all of these things, and why I am doing so, because this is the this is a matrix with which if you multiply, if you do the diagonalization, then what you will get reach to in the plus 45 minus 45 degree. We know that one unitary operator does so. Okay, so all of these are the concept of basic matrices. If you forgot, if you have forgotten these things, then you can always review it, and if you have any question you can ask to me. So now let us find this rho dash. For that, u dagger, that is the same thing again, then rho, then 1 1 1 minus 1, that is the u again. So it will become, if you do the calculation, 3 by 4 1 by 4 1 by 4 1 by 4, the same thing. So the probability, so the answer will be, you can see, if you take the projection on here, then only you will get the plus 45, because this is the probability of getting plus 45 with the plus 45. This is plus 45 minus 45, this is minus 45 plus 45, this is minus 45 minus 45. So the what is the probability that a photon in such a state gets detects at plus 45 degree polarized photon is 3 by 4. Probability of detecting the photon in plus 45 polarized photon is 3 by 4. Part B, what interferes in two photon interference? Very nice question. In a two photon interference, the different alternatives that lead to a two photon detection event, those are interfere actually. Problem C, it is asking what is the orbital angular momentum of a photon in the state psi equal to L equal to 1 to n CL. The only thing that can be said that if the orbital angular momentum of the photon is measured, one would find the photon to have orbital angular momentum of LH bar with CL square probability. These things I have already mentioned with in previous class with particular slide. You can revisit that also. If you forgot, maybe I can go once. See here it is written that in LG mode OM per photon is LH bar, and the corresponding to that the weightage of that L mode, it's what gives us the probability, and that is here the CL square. Okay. Now the D part D, if rho represents the density matrix corresponding of a quantum state, derive the quantum mechanical expression for the expectation value of an operator A. This is very interesting. You will learn that how much interesting and important it is eventually with the time, because from that on you don't need to calculate we don't need to do the tomography of the density matrix or the coherent state. We just can calculate the trace, that is the diagonal elements, and we can find the expectation value of an operator A. So let us know how to do that. So to present the density matrix rho as a sum of pure state ensemble, we can write rho in terms of psi its ensemble average, which can be written as pi psi I, where psi I represents the state vector of an individual pure state ensemble. And pi is its weightage in the sum, with pi summation of pi equal to 1. The expectation value of an operator A is given by the sum of the expectation values over all the pure state ensembles, and that can be written as psi A psi ensemble average. You all know that thing with the basic quantum mechanics. Now we will go further. I pi. Now these are the plain linear algebra and or bracket notation algebra, whatever you say, we will do so. Now we can write this as like this. We all know we can introduce, this is a theory of completeness and orthogonality, those things we use, and we can write something like this, because psi j pj is equal to 1, nothing else. So I j. Now it becomes pi psi j psi I a cap psi j, which equals to psi j I pi psi I a cap psi j. That becomes j equal to psi j rho a cap psi j. That becomes trace of rho a cap. So this is the answer. What it was told? It was told that to derive the quantum mechanical expression for the expectation value of for an operator. That is what we have done. Now problem 4. It is saying the density matrix of a single photon field is given by rho equal to this, while L is representing a single photon state with orbital angular momentum index L. Then calculate the azimuthal correlation W phi 1 phi 2 of the field and calculate the single photon detection probability. Let us do. So the density matrix has no off diagonal term, that is no correlation. From this we can see that this has no off diagonal term. That means from this we can understand that no correlation between different OM component. Therefore the azimuthal correlation W phi 1 phi 2 and the spectral density function SL are connected through a Wiener-Kenshin theorem given what we know, which is W phi 1 phi 2 W delta phi equal to summation of L equal to minus infinity to infinity SL e to the power IL delta phi. W delta phi equal to, if we do so, then what we will get? 1/4 minus I2 delta phi plus 1/4 e to the power minus I delta phi plus 1/4 e to the power I delta phi plus 1/4 e to the power I2 delta phi. Okay. Alright. Corresponding to minus 2 it is minus 2, corresponding to minus 1, corresponding to minus 2 it is minus 2, corresponding to minus 1 it is minus 1, corresponding to 1 it is 1, corresponding to 2 it is 2. This can be written as delta phi plus half cos 2 delta phi, which is cos delta phi plus cos 2 delta phi by 2. This is the answer, which is the azimuthal correlation function of the field. Now calculate the single photon detection probability. Calculate the single photon detection probability P phi. That is nothing but W phi phi, which is W delta phi equal to 0 equal to half plus half equal to 1. So the probability remains constant. So we have 4 problems divided into which is divided into 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 problems I have already solved. Now we will solve some more problem, because today our aim is to solve the problems. But before that, let us take some rest again, then we'll start solving this question. In the meanwhile, in between, you please read this problem and try to think yourself, then we'll start. Okay. So let us start our this problem 5. Where it is saying consider the one photon Michelson interferometer as shown here. The state of the photon at the source is psi equal to 0 to infinity v omega kate omega d omega, where omega kate represents one photon at frequency omega and v omega is the field amplitude of a stationary random field at frequency omega. Now, so that the probability of detecting a photon dA is given by this PA, which we need to prove, where K1 and K2 are the overall constant and T1 and T2 are the travel times of a photon in the two alternative path. So let us start solving this. Electric field at the detector. I teach you, or I told several times how to write these kind of fields at the output port of the beam splitter, so that we can proceed the further things. I have shown you with the Maxenter interferometer, even with the Michelson interferometer also. So we'll follow the same thing. I have described previously these things very well, that how to do any kind of analysis with the interferometers, any kind of like probability analysis or getting the total interference, all those things. So we'll just here use the same thing, and let us follow these things step by step. If you have forgotten or if you have missed some part, then please go visit the YouTube link videos, there you will get it again. So E plus T K1 E plus T minus T1 plus K2 E plus T minus T2. Therefore, the probability is PA equal to psi ensemble average. Okay. K1 star. I am doing everything very in step by step manner. I am not missing or jumping any step, such that there is no problem in understanding. And K1 E plus T minus T1 plus K2 E plus T minus T2. Now expanding and simplifying the above expression, so what we'll get is, try to follow the steps by yourselves. Now I will write what it will actually come, because this kind of steps we have done several times. This is nothing but we need to calculate each and every terms, multiplications, and finally we can write this. You don't even need to do the in between any calculation. This is just the next step only. This is minus plus, nothing else. Let me maybe shift it to there and rewrite it again. So this is the thing that is given in the question. We need to prove. So this is proved that this will be the probability of detecting a photon at dA. Now the next question, it is asking, use the representation E plus T equal to integration 0 to infinity omega to the power minus I omega t d omega, and so that E minus T is equal to 0 to infinity a dagger omega to the power I omega t d omega. Okay, let us do that. Since E minus T is the operator representing the negative frequency part of the field, therefore it can be defined like this manner. Okay. Now substituting omega dash as omega, then we get E minus T equal to infinity to 0 a minus omega dash to the power I omega dash t minus omega equal to omega equal to minus omega equal to omega. So omega dash t and minus of d omega dash, then what we get is 0 to infinity a minus of omega dash to the power I omega dash t d omega dash. Okay, no issue here, just I have substituted minus omega in place of omega and rewritten the terms and moved the 0 minus infinity to 0 integration to 0 to infinity. Now since now it is a Hermitian operator, et is Hermitian operator, and we have this, therefore E minus t equal to 0 to infinity a dagger omega e to the power I omega t d omega. Right. Now the question is saying, now we have figured out for the case B. Now for this case C, it is saying, since the field is stationary, we can write V star omega V omega equal to S omega delta omega minus omega dash, where S omega is the spectral density of the field using the above relation, so that psi is minus T1 is that means this correlation is equal to 0 to infinity S omega to the power I omega t minus I omega tau d omega. That's very easy, right? Like we can do this. What we need to do, we need to find out E plus T minus T2 whatever it is told in that manner, and then we substitute that those things in the in this function, this correlation function, and then we have the stationary random source here, so we will substitute delta Dirac delta function, and we will get to reach there. So let us follow the steps. We know that a dagger omega dash equal to vacuum delta omega minus omega dash. So we'll use this. These are the letter operator, a plus and a and a dagger that we know, and what are the if we operate a dagger, ladder A or a dagger anywhere, then what will be the result, that we have already known, we are well aware about, because those things also were used in case of spontaneous parametric down conversion derivation. So now, sorry, before going to that correlation directly, we need to substitute this to the previous equation and need to see that what it is actually happening. So now I am substituting the above this thing. So now we can write okay. Now for stationary random source, we have v star omega dash v omega equal to s omega delta omega minus omega dash. We'll substitute this and we'll get s omega delta omega minus omega dash e to the power I omega dash t minus t1 to the power I omega minus I omega t minus t2 d omega dash, which is equal to 0 to infinity s omega to the power minus I omega tau d omega. So whatever it is told, it is proved. All right. So these are the questions that I wanted to solve today, and this slide is already provided to you. With the slides, it is already updated, and I will provide you the today's solutions and notes and all of those things, and those will be those will be those are already there, and those will be there in the drive folder link. But this another 7 problems I have given already to you. This I will solve in the next class, but I just want that you go through all of this and try to do it by yourself. That's why it is given, so consider this as homework. Okay, so this was it for today. We have done lots of question, I think, because that was one of the main purpose for today's class. 12, 13, 14, 15 questions we have already solved, and you need to like, as you guys are feeling problem in the facing problem in the problem solution or the assignments or the quizzes, that's why I did so. And if you have any problem, do write me in the mail, through mail. Mail is already given in the chat box. You can also contact via or write into the YouTube YouTube comment section, or use ask a question portal. Lots of people ask question there, we answer there. Lots of people mail actually, those who are actually not able to join somehow, and they used to finally they use the YouTube videos as their source to study these things, because I think the lectures as well as this kind of these sessions both are important for getting good marks in the quizzes, assignments, and the final examination. So this was it for today's class. Let's say goodbye. I will See you in the next class in week 9. We have already completed 2/3 part of the course, and best of luck and for your journey. I hope you guys are working hard for the for the examination also. So let's meet at the next class. Bye.